Omega naught equal to 2 pi f naught over t. Exactly. All is equal to 2 pi over t is really the sampling frequency. So equal to f naught over sampling frequency. Right? Is that clear? Yes. And now assuming that I'm going to design a line N filter and it is a causal filter. So it's causal filter, that means N would go from 0 to N minus 1. Right? The filter has a sample going to positive direction. So the question is, I really have to find out this number. Right? Finding out this number, I can plug into this formula and I can run the systems. So find this number is very, very difficult. Well, that is a problem of filter design. And we have one technique before, we just select an ideal filter and we window them, right? With some correct shift and delay. Now another technique now is, say, in certain applications, you know that you want to have an ideal filter. So maybe going back to the ideal filter, that is ideal filter to pi here. So that is ideal filter. H of omega ideal. And you can easily see the problems that we cannot have is we only have n degree of freedom. N degree of freedom to play. And we want to get this, so this n degree freedom giving us some filter h omega. And this h omega is the function that have value for every value of omega. So we cannot twist all of these numbers so that this thing matches what exactly every omega. Right? So that's the thing. So if I have n degree of freedom here, what is the maximum I can hold for? What is the maximum I can match? N, right? So I can have n, then maybe now I can specify in this here, I want to have h of omega equal to h of the design filter omega for omega equal to some omega k. K go from 0 to n minus 1. That's the best I can hope for. Right? So now, for example, I want this very critical location. This location here, I want the filter have to match. I want the filter have to match. Right? So that I want the filter, my ideal filter go through those. And what I hope for is, okay, so the actual filter, it would go through this point. So these are the points that it crossed. It match the ideal filter. But in between, I have no other guarantee. I just hope that, okay, because if this thing is a finite line, so you can easily show that this thing here is a continuous function. So we're going to very, very continuously here. So if it is, okay here, maybe nearby is not too bad. That is the idea. Okay. So if I have that, then what? Okay. So maybe the question is early on, the number of degree of freedom. Maybe you can write them down explicitly now. So we erase from the beginning here. So in the technique with so-called frequency sampling, right? Frequency sampling, you can see that I sample the frequency of the ideal filter. I sample this thing, but only at those certain moments in frequency. I enforce it equal to I enforce this filter I'm going to design equal to this ideal filter. Right? What do we have? We have h of omega, and we know that that is our desired filter. our real filter, and its summation in n go from 0 to n minus 1. It is h and e j omega n. So now enforce constraint that I have h of omega k equal to this h design of omega k. Right? So they are the sequence of number. And here is I have to enforce. Right? For k go from 0 to, maybe I want to make it more general here, to k minus 1. Enforcing that would leave you something like this. I will have a summation of h of n e j omega k of n. Here n go from 0 to n minus 1 and equal to this h d of omega k. Alright? Now in this case here, let me circle. These are the unknown. Right? These are one that I want to find. These are one that I want to really get. But everything else is known, right? Because I know this thing, I know this value. So then, what is this? It's just really a linear system, right? And then we can solve. So this is amount to this is just simply a system of linear equation. Right? So this, you can see that this is system of linear equation. How many unknowns? N unknowns. How many equations? K equations, right? N unknown K equation. Right? Because I have this thing here for K, from 0 to K minus 1. And these are unknown. Right? So that's what I say early on. You can hope for at best enforcing about N. You can have more, but then you have to solve a least square solution. You can have a less, you may have to equal something else. Right? It is a thing that you have to solve a linear system equation. Okay? What do you predict? What happened? What kind of case is that? We have something like Fourier transform, right? Remember, taking the discrete Fourier transform is simply sample the DTFT at those equal space locations. Right? So the edge, this edge here, the edge of omega k, the edge of omega k is simply equal to the edge of k. And this thing here is the DFT of Hn, taking the DFT of like n. Right?
That is the left side.
Of what?
That is omega k.
No.
And now instead of enforcing only a certain point, I want to enforce anywhere but now with some tolerance. I allow them to wiggle, but I want to control that wiggle. So the thing here, for example, I have this filter and I will say that, okay, here's my ideal filter. But now I'm saying, actually, I really want from 0 to SP. I really want the signal go through. From omega s to pi, I want it going to be stopped. So this is, from here to here, is so